Imagine, if you will, that you are not human. Imagine that you have spent the last several thousand years traveling between star systems, watching civilizations rise and collapse, studying the way young species develop their understanding of the universe around them, and you have arrived at a particular moment in the intellectual development of a small, curious, bipedal species living on a moist, oxygen-rich world orbiting an unremarkable yellow star, located roughly 2/3 of the way out along one of the spiral arms of a galaxy these creatures have decided to call the Milky Way. You are an observer. You are patient. You have seen many species struggle with the same concepts, wrestle with the same confusions, bump their collective heads against the same walls of misunderstanding. And you have found, over centuries of watching and listening and occasionally communicating with young civilizations, that mathematics is not always the first door through which genuine understanding enters. Mathematics is a precision tool, yes. It is extraordinary in what it can accomplish, in the predictions it allows, in the certainties it produces when wielded by a mind that has trained long enough to wield it properly. But mathematics, as you have observed, is also a language that many beings never learn fluently, and a great truth locked behind a language barrier is not fully shared. And so you have decided, in this particular instance, sitting comfortably in whatever passes for a comfortable posture among your kind, looking at this small blue world and its eager inhabitants, to explain one of the most magnificent and terrifying features of the universe in a way that requires no equations, no calculus, no understanding of differential geometry, no prior knowledge of tensor fields or quantum field theory in curved space-time. You are going to explain black holes the way a truly patient elder would explain anything important to someone who is young and curious and deserves to understand. You begin not with the black hole itself, because beginning with the black hole itself would be like beginning a story at its most dramatic moment, and stories told that way often leave the listener confused about how everything got to that point. You begin instead with something simpler, something the humans already know, something they have known in their bones since the first of their ancestors stood up on the savannah and watched the sky darken at night while a fire crackled nearby. You begin with light. Light is the fastest thing in the universe, not the fastest thing that humans have built, not the fastest thing they have imagined in their science fiction stories, but the fastest thing that is physically possible for anything to travel. This is not a limitation of technology. This is not a constraint that will someday be overcome with cleverness or engineering. This is a fundamental feature of reality, baked into the structure of space-time itself, as absolute and non-negotiable as anything gets. Nothing with mass can ever reach the speed of light, and nothing can exceed it. Light itself, composed of massless photons, travels at exactly this cosmic speed limit, and it does so in every direction, constantly, relentlessly, without ever slowing down in the vacuum of space. Now, the humans know about gravity. They have known about it in a practical sense since before they had language to describe it. A stone thrown upward returns to the ground. Water flows downhill. The moon circles the earth. The earth circles the sun. All of this is gravity. Their brilliant thinkers have formalized it, first in one way, and then in a deeper, more accurate way. And they now understand gravity not merely as a force pulling things toward each other, but as something more subtle and profound. Gravity, in the deeper understanding, is a consequence of the way mass and energy warp the fabric of space-time itself. This sounds abstract, but think of it this way. Imagine that you stretched a large, thin rubber sheet horizontally in the air, perfectly flat, perfectly taut. Now imagine placing a heavy ball in the center of this sheet. The ball sinks, and the sheet curves downward around it, forming a depression, a funnel shape, deeper near the ball and flattening out toward the edges. Now take a smaller ball and roll it across this curved sheet. It does not travel in a straight line because the sheet is not flat. It curves toward the depression. If you roll it with exactly the right speed, in exactly the right direction, it will circle around the depression, never quite falling in, never quite escaping either. This is, in a rough and imperfect but genuinely useful way, what gravity does to the paths of objects moving through space. The mass of a large object curves the space-time around it, and other objects, moving through that curved space-time, follow paths that appear to bend toward the massive object. The planets orbit the sun not because some invisible hand is yanking them inward, but because they are following the most natural paths possible through a region of space-time that the sun's enormous mass has curved. Now here is where things get interesting. Interesting in the way that makes even beings as old and widely traveled as you still feel a kind of quiet wonder. What if the depression in that rubber sheet got deeper? What if you placed a heavier and heavier ball in the center? The depression would grow. The curve would steepen. Objects rolling across the sheet would find it harder and harder to escape the depression, requiring more and more speed to roll up the steep sides and get away. Now what if the depression became infinitely deep? What if the walls of the funnel became perfectly vertical and then tipped past vertical, curling back inward on themselves? In that case, nothing rolling across the sheet would be able to escape, no matter how fast it was rolling. It would always curve back in. It would always fall. This is the fundamental concept at the heart of what a black hole is. A black hole is a region of space where gravity has become so enormously, inconceivably strong that not even light, the fastest thing in the universe, can escape from it. The fabric of space-time has been curved so severely, so completely, that every possible path forward, for anything, points inward. There is no direction that leads out. There is only in. But how does such a thing come to exist? This is the part of the story that requires you to talk about stars, and specifically about what stars are and what happens to them when they die. Across the universe, scattered through every galaxy in their billions and trillions, stars live long lives measured in millions or billions of years. They are, at their cores, enormous engines of fusion, places where hydrogen atoms are squeezed together so tightly, under such crushing pressure, and at such searing temperatures, that they merge and become helium, releasing enormous amounts of energy in the process. This energy, constantly generated at the core, pushes outward, and this outward push is precisely balanced by the enormous gravity of the star's own mass pulling inward. A star is a perpetual balancing act, an arm wrestle between the explosive outward pressure of nuclear fusion and the crushing inward pull of gravity. For most of a star's life, these two forces maintain a kind of equilibrium. The star shines. It warms the planets around it if it has any. It simply exists in this balanced state. But fusion requires fuel, and fuel even in enormous stellar quantities, eventually runs out. The process actually goes through several stages, as the star burns through successive layers of fuel, first hydrogen into helium, then helium into carbon and oxygen, then through heavier and heavier elements, all the way up the periodic table in the cores of the most massive stars. Each stage of burning provides less energy than the last, and each stage passes more quickly. The final stages of a truly massive star's life can proceed with startling rapidity, the inner core going through dramatic changes in years, months, days. And then the fusion stops. The fuel is gone. The outward pressure disappears. And in that moment, gravity wins. What happens next depends on how massive the star was. For stars like your sun, the human sun, the collapse is relatively gentle by cosmic standards. The outer layers drift away, and the core collapses into something called a white dwarf, a city-sized ball of extraordinarily dense matter, where a teaspoon of material would weigh roughly the same as an automobile. The white dwarf does not collapse further because of a quantum mechanical pressure, a consequence of the strange rules that govern the very small, which prevents the electrons in the dense matter from being squeezed any closer together. The white dwarf simply sits there and slowly cools over billions of years. Dramatic enough, but not what you are here to explain today. For more massive stars, the story is more violent. The core collapses more rapidly, and the outer layers, initially falling inward, bounce off the suddenly rigid collapsed core with tremendous force, producing an explosion of almost incomprehensible power. A supernova, which can briefly outshine an entire galaxy of hundreds of billions of stars. The core that remains after this catastrophic explosion can be something called a neutron star, where the density is so extreme that protons and electrons have been forced together to form neutrons, and the entire core, several times the mass of your sun, has been compressed into a sphere roughly 20 kilometers across. The density of a neutron star is roughly equivalent to the density of an atomic nucleus. Imagine compressing the mass of a mountain into something the size of a grain of sand, and then imagine doing that with an entire star. But for the most massive stars, even this is not the end of the collapse. The quantum mechanical pressure that holds neutron stars together has a limit. Push past that limit, accumulate enough mass, and gravity wins again. The collapse continues, and it does not stop. When a stellar core collapses past the point where even neutron degeneracy pressure can halt it, the matter continues collapsing inward. It collapses into a single point of infinite density, or at least what the mathematics suggests would be infinite density, a singularity. The space around this singularity is so severely warped by gravity that there exists a boundary, a surface not made of anything material, not a wall or a membrane, but simply a location in space, inside which nothing can escape. This boundary is called the event horizon. Everything inside the event horizon is lost to the outside universe forever. No information, no light, no matter, no signal of any kind can cross back out through the event horizon. It is a one-way door. The event horizon is where the black hole, in a sense, truly begins, because the event horizon is what makes a black hole black. A black hole cannot be seen directly. There is no surface to look at. There is no glow. The region inside the event horizon emits nothing, because nothing inside can get out. What you see when you look in the direction of a black hole is an absence, a darkness, a region where the stars behind it are distorted and bent around it by gravity, their light curving around the event horizon like water swirling around a drain, but where the region itself is dark because no light emerges from inside it. This is a strange thing to try to visualize. You are accustomed, as a spacefaring being, to seeing objects because they either produce their own light, like stars, or they reflect light, like planets and moons. But a black hole reflects nothing. It absorbs everything that falls into it. If you could see the universe from outside a black hole, you would see an almost perfectly circular patch of darkness in space, surrounded by a halo of bent and distorted light. The images of stars and galaxies, whose light has been curved around the event horizon on its way to your eyes. Astronomers on Earth have actually managed to capture images of these dark regions surrounded by their glowing halos of bent light, confirming what the theory predicted. Now let us talk about what the event horizon actually means, because this is where the strangeness of black holes truly begins to reveal itself, and where the human instinct to think in familiar, everyday terms begins to lead people astray. The event horizon is not a physical surface. If you were falling toward a black hole, you would not feel a bump or encounter any resistance when you crossed the event horizon. You would not even necessarily know that you had crossed it. You would simply continue falling. But once you had crossed it, your fate would be sealed. Every path available to you would lead inward. You could fire your rockets in any direction. You could try to flee in any direction, and you would still continue to fall toward the center. This is not because of some force pushing you inward. It is because inside the event horizon, the curvature of space-time is so severe that all possible future directions lead toward the singularity. In a sense, inside a black hole, the singularity is not in a direction of space. It is in a direction of time. It is your future, and you cannot avoid your future any more than you can avoid the passage of time. This is deeply counterintuitive, and it should be, because nothing in the everyday experience of a planet-bound organism prepares them for this idea. But it is worth sitting with. Time and space, as the deepest understanding of physics reveals, are not entirely separate things. They are woven together into a four-dimensional fabric called space-time. Normally, in everyday life, time flows forward at a steady rate, and you have freedom to move in any of the three dimensions of space. You can go left or right, forward or backward, up or down. Inside a black hole, the curvature of space-time is so extreme that the geometry works differently. The dimension that, outside the event horizon, pointed toward the singularity behaves like a time dimension. And you cannot move backward in time. You cannot stop time. You can only move forward through it. And so, inside a black hole, you can only move forward toward the singularity in exactly the same way, and for exactly the same reason that you can only move forward through time. This gives some idea of the true nature of a black hole. It is not simply a very strong gravitational field, the way a planet has gravity, and a star has stronger gravity. It is a place where the nature of space-time itself has been so radically altered that the concepts of space and time as you experience them outside do not apply in the same way inside. Now, you know that the humans have a tendency to ask a particular question at this point, and it is a good question, a natural question, the kind of question that reveals genuine curiosity and a desire to understand beyond the surface. The question is, what happens when you fall in? What does it look like? What does it feel like? What would an observer experience? This turns out to have several different and deeply interesting answers, depending on who is doing the observing. If you are watching someone fall into a black hole from a safe distance outside, you will see something strange. As the falling person approaches the event horizon, you will see them appear to slow down. Their image will become dimmer and redder. The light that reaches you from them has to climb out of a deepening gravitational well to reach you, and this costs the light energy, shifting it toward the red end of the spectrum. And as the falling person gets very close to the event horizon, the image slows down further and further, growing dimmer and redder, until it seems almost frozen, hovering just above the event horizon, fading away like a ghost. The person never appears, from your distant perspective, to actually cross the event horizon. They seem to hang there and fade. But this is an illusion created by the finite speed of light and the extreme warping of space-time near the event horizon. The last light that ever reaches you from the falling person was emitted just before they crossed. Light emitted after they crossed can never reach you, so you never see them cross. But they did cross. From their own perspective, they crossed the event horizon at a normal rate of time, experienced nothing dramatic at the moment of crossing, and continued to fall. From the falling person's perspective, the experience is also deeply strange, but in different ways. As they approach the black hole, they will see the universe around them appear to change. The stars of the outside universe will appear to crowd into a brighter and brighter circle overhead, as the extreme bending of light funnels all the images of the outside universe into a shrinking cone. Below them, the darkness of the black hole will expand, filling more and more of their view. The tidal forces, the difference in gravitational pull between different parts of their body, will increase as they approach. For a very large black hole, these tidal forces at the event horizon might be gentle enough that a person could cross without being torn apart. For a smaller black hole, the tidal forces at the event horizon would be so extreme that the falling person would be stretched along the direction of fall and compressed from the sides, a process that astrophysicists have given the rather wonderful name of spaghettification. The person would be stretched like a strand of cosmic spaghetti before they even reached the event horizon of a small black hole. Once inside, if we imagine the person has survived crossing the event horizon of a large black hole, they are in the inside of the black hole. What is there to see? What is it like? The honest answer is that nobody knows with certainty, because nothing has ever come back from inside to tell us, and the mathematics, which works so well outside black holes, breaks down at the singularity. The singularity is a place where the current theories cannot describe what happens, where the numbers literally go to infinity in ways that tell physicists their theory is incomplete. It is the edge of the map, the place where the chart ends, and there is nothing written. Not even the notation here, "there be dragons," because even that would imply something is known about what is there. What the mathematics suggests is that the singularity is a place of infinite density, infinitely compressed matter, where space-time itself ends or ceases to have meaning. Many physicists suspect that a more complete theory of physics, one that successfully merges gravity with quantum mechanics, would reveal that the singularity is not truly infinite, that something happens at extremely small scales that prevents genuine infinity. But what that something is remains one of the deepest unsolved problems in all of science. Let us step back from the interior of black holes and talk about some of the other remarkable properties they have, because black holes are not simply holes. They are extraordinary objects with behaviors that continue to surprise even those who have studied them for a long time. Black holes are extraordinarily simple objects in one respect. When you have a black hole and you want to describe it completely, you need only 3 numbers. How much mass does it have? How much electric charge does it carry? How fast is it rotating? These 3 numbers, mass, charge, and spin, completely determine every property of a black hole that can be observed from outside the event horizon. Everything else that ever fell into the black hole has been lost, as far as external observers are concerned. It does not matter whether you made your black hole by collapsing a star made of hydrogen or a star made of iron, or by somehow cramming in an enormous collection of rubber ducks. The black hole that results, if it has the same mass, charge, and spin, is identical in every externally measurable way. This remarkable simplicity is captured in a principle called the no-hair theorem, the idea being that black holes have no distinguishing features, no hair, beyond these 3 numbers. This simplicity is itself a kind of strangeness. In the ordinary world, you can tell a great deal about what something is made of, what its history has been, what processes formed it. A rock reveals, to careful examination, the geological and chemical processes that shaped it over billions of years. A living being carries in its body the record of its ancestry and its history. But a black hole discards all of that. It is the ultimate anonymizer. All the complexity, all the history, all the variety of whatever fell into it is reduced to 3 numbers. This raises a profound and deeply interesting question, one that has occupied some of the most brilliant minds working on physics for decades. If information about what fell into a black hole is truly lost, never to be recovered, this seems to conflict with a very deep principle of physics, which says that information is never truly destroyed, that in principle, if you know the complete state of a system now, you can calculate what it was in the past, that the universe keeps track of everything. Most physicists believe in this principle deeply, not just as a mathematical nicety, but as something fundamental about how reality works. And yet, if you throw a book into a black hole, the information in that book seems to be gone forever. This puzzle is called the black hole information paradox, and it is one of the great unresolved questions in fundamental physics. There have been proposed resolutions, and one of the most intriguing involves something called Hawking radiation. In the early 1970s, a brilliant physicist named Stephen Hawking, working on the intersection between general relativity, which describes gravity, and quantum mechanics, which describes the behavior of the very small, discovered something remarkable and completely unexpected. Black holes are not entirely black. They glow very faintly, with a temperature that depends on their mass. Smaller black holes glow hotter. Larger black holes glow cooler, but they all glow, and as they glow, they lose energy. And losing energy means losing mass. And losing mass means the event horizon shrinks, and eventually, in principle, a black hole can completely evaporate. For any black hole of stellar mass or larger, this process takes an almost incomprehensibly long time, far longer than the current age of the universe. So no actual black hole formed from a stellar collapse is expected to have evaporated yet. But the principle is important, and the implications profound. How does this radiation arise? It comes from the strange behavior of quantum fields in curved space-time near the event horizon. The vacuum of space, according to quantum mechanics, is not actually empty. It seethes with what are called virtual particles, pairs of particles and their antiparticles that pop into existence together and annihilate each other again almost immediately. Borrowed energy from the quantum vacuum that must be paid back. Normally, this process has no observable effect, but near the event horizon of a black hole, something strange happens. Occasionally, one particle of a virtual pair falls inside the event horizon, while the other escapes. The one that escapes becomes a real particle, and the energy it carries has to come from somewhere. It comes from the black hole itself. The black hole loses a tiny amount of mass with each such event. Over an enormous span of time, the black hole shrinks and eventually evaporates entirely. And what happens to the information about everything that fell in? Does it come out encoded in the Hawking radiation? Is it lost forever? Is there something deeper going on? Some process that returns the information to the outside universe in a form that is, in principle, recoverable, even if practically impossible to decode? This remains unsettled. The resolution of this paradox likely requires the unified theory of quantum gravity that physicists are still searching for, and it is one of the main motivations driving that search. The answer, whatever it turns out to be, will tell us something deep and fundamental about the nature of reality. Now let us talk about the different kinds of black holes, because black holes are not all the same, and the variety of black holes that the universe seems to contain is itself remarkable. The kind of black holes we have been discussing so far, the ones formed from the collapse of massive stars, are called stellar mass black holes. They range in mass from a few times the mass of your sun up to perhaps a few tens of times the mass of your sun. They are the most commonly encountered type, the ones physicists feel most confident about in terms of their formation mechanism. But at the centers of galaxies, including the galaxy in which the humans live, there exist things called supermassive black holes. These are black holes with masses ranging from millions to billions of times the mass of the sun. The supermassive black hole at the center of the Milky Way is called Sagittarius A star, and it has a mass of about 4 million times that of the sun. The supermassive black hole at the center of a galaxy called Messier 87, the first black hole whose shadow was directly imaged by the Event Horizon Telescope project in 2019, has a mass of roughly 6.5 billion solar masses. Its event horizon is larger than the entire orbit of Pluto around the Sun. How did supermassive black holes form? This is another open question in astrophysics. The most straightforward answer would be that they grew through repeated mergers of smaller black holes and through the accretion of enormous amounts of gas and dust over billions of years. But this straightforward answer runs into some timing problems, because we can observe supermassive black holes in very early galaxies, when the universe was only a tiny fraction of its current age, and it is not obvious that there was enough time for ordinary stellar mass black holes to grow by accretion to the enormous masses we see. Various alternative formation mechanisms have been proposed, including the direct collapse of enormous clouds of gas in the early universe. But the question of how supermassive black holes formed and how they grew to their current sizes so quickly is an active area of research. There may also be intermediate mass black holes, with masses between a few hundred and a few 100,000 solar masses. filling the gap between stellar mass and supermassive black holes. Evidence for these has been harder to obtain, but there are hints and some stronger candidates. And there may have been primordial black holes formed in the very early universe, in the chaotic first moments after the Big Bang, when density fluctuations could have been large enough to cause regions to collapse directly into black holes without going through the stellar route. The universe appears to be populated with black holes at many different scales, and these objects play important roles in the evolution of galaxies. The supermassive black holes at galactic centers interact with the gas around them in complex ways. When a black hole is actively consuming gas and dust, material forms an accretion disk, a swirling structure of matter spiraling inward, heated by friction and compression to extraordinary temperatures, emitting enormous amounts of radiation across the entire electromagnetic spectrum. Some of the most luminous objects in the visible universe are powered by supermassive black holes actively consuming material. These objects, called quasars, can outshine their entire host galaxies of hundreds of billions of stars. The energy comes not from nuclear fusion, as in stars, but from the gravitational potential energy released as matter falls deeper into the gravitational well of the black hole. Matter falling toward a supermassive black hole can release up to 10 times more energy per unit mass than nuclear fusion can. A black hole in an active feeding state is one of the most efficient energy conversion mechanisms in the known universe. And black holes do more than simply consume. The accretion of matter can produce powerful jets, focused beams of particles, and radiation launched from near the black hole's poles at near-light speeds and extending for thousands or even millions of light years into the surrounding space. These jets can heat and stir the gas in the surrounding galaxy and the space between galaxies, affecting whether that gas can cool and collapse to form new stars. In this way, the supermassive black hole at a galaxy's center can regulate the rate at which the entire galaxy forms stars, influencing the structure and evolution of the galaxy on scales millions of times larger than the black hole itself. Black holes, despite consuming everything that falls into them, are not simply absorbers. They are powerful agents of change in the universe around them. Let us also speak about what happens when two black holes collide and merge, because this is one of the most dramatic events the universe has to offer, and it leads to something that connects directly to an extraordinary observational achievement of recent decades. When two black holes orbit each other, they emit gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, produced by accelerating masses, propagating outward at the speed of light, carrying energy away from the system. You can think of them as analogous to the ripples that spread outward when a stone is dropped into still water, except that instead of rippling across the surface of a pond, gravitational waves ripple through the fabric of space-time itself, slightly stretching and squeezing the distances between points in space as they pass. As two black holes orbit each other and emit gravitational waves, they lose energy. And as they lose energy, their orbit shrinks. They spiral closer and closer together. Their orbital period shortens. They spin around each other faster and faster. The gravitational waves they emit become more frequent and more powerful. This in-spiral and merger process, seen from the outside and described in terms of gravitational wave emission, looks like a chirp, a signal that rises in frequency and intensity, reaching a peak at the moment of merger, and then ringing down as the newly merged black hole settles into its final state, its final shape, emitting one last burst of gravitational waves as it does so. These gravitational waves were first directly detected in September of 2015 by the LIGO detectors, instruments that use lasers to measure the tiny stretching and squeezing of space as gravitational waves pass through them. The first detection was the signal from two stellar mass black holes, each with tens of solar masses, that had spiraled together and merged about 1 billion light-years away. The gravitational wave signal that arrived at Earth had been traveling for 1 billion years, and the stretching and squeezing it produced when it arrived was measured in units, smaller than 1/10,000th of the diameter of a proton. The precision of this measurement is one of the most remarkable technical achievements in the history of human science. Since that first detection, many more mergers have been observed, a growing census of black holes and neutron stars colliding and merging in the universe, opening a new window on the universe, a way of listening to the cosmos through gravitational waves rather than looking at it through electromagnetic light. This is from the perspective of a spacefaring civilization, a very young but enormously promising way of learning about what the universe contains. Now, you want to address something that often comes up when explaining black holes to young civilizations, a category of misunderstanding that takes several forms but shares a common root. The misunderstanding is that black holes are somehow dangerous to everything around them, that they are cosmic vacuum cleaners sucking up the universe, that having a black hole in your galaxy or near your solar system is a sentence of doom. This misunderstanding is understandable, but incorrect. A black hole is not a cosmic vacuum cleaner. It does not reach out and grab things that are not already heading toward it. It does not have infinite range. Its gravitational influence is exactly what you would expect for an object of its mass. If you could somehow replace the sun in the center of your solar system with a black hole of exactly the same mass, the planets would continue to orbit exactly as they do now. Nothing would change about the orbits. Earth would not be sucked in. The only difference would be the absence of sunlight and heat, which would of course be catastrophic for life on Earth, but not because of any special black hole sucking property. Simply because the sun would no longer be producing light. A black hole is only dangerous if you get close to it. Very close. Within a distance where the tidal forces are significant. Within a distance where the curvature of space-time begins to deviate markedly from what you experience in the weak gravity of everyday life. For a stellar mass black hole, this danger zone is relatively small. For a supermassive black hole of billions of solar masses, the danger zone is much larger in absolute terms, though the tidal forces at the event horizon of a truly giant black hole are actually weaker than at the event horizon of a stellar mass black hole, because the event horizon is so much larger that the gradient of gravity across it is gentler. The universe is vast, and black holes, though numerous by some measures, are tiny compared to the distances between them. Your solar system is in no danger from any known black hole, all of which are at distances of thousands of light-years or more. There is, of course, the supermassive black hole at the center of your galaxy, Sagittarius A star, which is about 26,000 light-years away from your sun. It is enormous in mass, but it is not currently in an active feeding state. It is relatively quiet, consuming very little material, and it will remain extremely far away. Your solar system orbits around the galactic center along with hundreds of billions of other stars, and will continue to do so for billions of years without any direct interaction with the central black hole. Let us return now to something that you find genuinely wondrous about black holes, something that takes the story beyond physics and into something almost philosophical, or at least into territory that touches on the deepest questions about the nature of reality. Consider what a black hole tells us about our universe. The very existence of black holes tells us that space-time is not merely a passive backdrop against which events occur. Space-time is a dynamic, physical thing that can be warped, curved, stretched, and in extreme cases, torn. The singularity at the heart of a black hole, or whatever actually exists there, represents the place where the curvature becomes so extreme that our current understanding breaks down entirely. It is a crack in the foundation of our best theories, a place where the math that has served so well everywhere else stops working. This is not a failure of science. This is science working exactly as it should, revealing its own limitations and pointing toward what remains to be understood. Black holes are the universe's way of demonstrating that there is more to learn. They are the places where the known and the unknown meet, where the physics that is understood and tested meets the physics that is yet to be discovered. The resolution of the black hole information paradox, the development of a complete theory of quantum gravity, the understanding of what actually happens at a singularity, these are not just technical puzzles. They are hints at a deeper, more complete understanding of what reality is, of what space and time actually are at the most fundamental level, of how the universe keeps track of itself. When you look at a black hole, whether with your eyes, with instruments, with mathematics, or simply with your imagination, you are looking at a place where the universe shows its seams. You are looking at a place where the fabric of everything is pulled so tight that it begins to reveal its own underlying structure. And the underlying structure, when it is finally understood, will probably be something that no species in their early scientific development could have predicted, something stranger and more wonderful than the black hole itself. The history of scientific discovery is full of this pattern. Each time a profound mystery is resolved, the resolution does not make the universe smaller and more ordinary. It makes it stranger and more vast. When Newtonian gravity was revealed to be an approximation of something deeper, general relativity, the universe did not become simpler. It became richer, with curved space-time and geodesics and the possibility of black holes. When quantum mechanics was discovered and the probabilistic, non-deterministic nature of the very small was revealed, the universe did not become more predictable. It became more layered, more subtle, full of superpositions and entanglement, and the strange refusal of particles to commit to definite states until observed. Each layer of understanding added depth, added strangeness, added wonder. The resolution of the mysteries surrounding black holes will do the same. As a species that has been watching civilizations develop for a long time, you can say with some confidence that the discovery and understanding of black holes, however incomplete that understanding currently is, represents something significant in the intellectual development of any civilization. The moment when a species begins to seriously grapple with the existence of objects, where space-time itself breaks down, where the known laws of physics reach their limits, where the concepts of space and time themselves become strange and unfamiliar, that moment marks a kind of maturity. It is the moment when a civilization moves from describing and measuring the universe to genuinely trying to understand what it is, at the deepest level. The humans have reached this moment. They have not only predicted the existence of black holes mathematically, but they have observed them, measured them, listened to them through gravitational waves, imaged their shadows with linked radio telescopes spanning the entire diameter of their planet. They have begun to probe the deep mysteries that black holes present. They have brilliant people dedicating their lives to resolving the black hole information paradox, to developing quantum gravity, to understanding what happens at singularities. This is the work of a civilization that is genuinely curious about reality and willing to follow that curiosity wherever it leads, even into the most extreme and counterintuitive corners of the universe. And what is most remarkable, from your perspective as a patient, ancient observer, is that the most important insights about black holes have come not from just following the mathematics wherever it led, but from stepping back and asking what the mathematics actually means. From asking not just what the equations predict, but what those predictions tell us about the nature of space and time and matter and information. The physicists who made the greatest contributions to the understanding of black holes were people who took the mathematics seriously as a description of reality, who did not dismiss strange predictions as mathematical artifacts, but said, if the mathematics predicts this, then reality is that strange, and we need to understand it. This willingness to follow reality wherever it goes, even when it contradicts intuition, even when it demands the revision of deeply held beliefs about space and time, even when it requires sitting with profound uncertainty about what lies at the singularity, or whether information is truly lost. This is the heart of scientific inquiry. Black holes have been one of the most powerful drivers of this inquiry in the history of the human science, pushing physicists to think harder and more deeply about the nature of reality than almost any other phenomenon. So when you explain black holes without mathematics, what you are ultimately doing is telling a story about what the universe is capable of. You are saying that the universe contains places where gravity has won so completely that nothing escapes. Not light, not information, not the record of whatever fell in. You are saying that these places are not simply very strong gravitational fields, but genuine alterations in the structure of space-time, places where the directions of space and time become scrambled, where the future is not a direction in time, but a location in space, inescapable and absolute. You are saying that these places are born from the deaths of the most massive stars, that they exist in enormous varieties, from stellar to supermassive, that they influence the galaxies they inhabit, that they merge and produce ripples in space-time itself that can be heard across 1 billion light-years. You are saying that they glow, faintly, through a quantum process that may hold the key to resolving a deep conflict between two of the most successful theories in all of science. You are saying that they are, in every sense of the word, one of the most extraordinary things in the universe. And you are saying that they are not really holes at all. They are not empty spaces, not absences. They are, in a very real sense, the most present, most dense, most gravitationally dominant structures in the universe. A black hole contains so much matter compressed into such a small space that the very fabric of reality around it is transformed. Calling it a hole is in some ways the opposite of the truth. It is more like an overwhelming presence, a concentration of existence so intense that it reshapes everything around it, that it bends the paths of light and matter for vast distances, that it warps the measure of time itself so that clocks near a black hole tick more slowly than clocks far away. This last point, the slowing of time in a gravitational field, is worth dwelling on, because it is one of the most philosophically striking predictions of general relativity, and one that has been confirmed to extraordinary precision. Time passes more slowly in a stronger gravitational field. Near the surface of Earth, this effect is tiny but measurable, and it actually has to be corrected for in the GPS satellites that orbit Earth, because their clocks, experiencing weaker gravity at their orbital altitude, run slightly faster than clocks on the surface, and if this were not corrected, the GPS system would quickly accumulate errors that would make it useless for navigation. Near a black hole, this time dilation becomes extreme. At the event horizon of a black hole, time, as seen from the outside, stops entirely. The person falling in, from the outside observer's perspective, freezes at the event horizon and fades away. Time itself, in this sense, hits a wall at the boundary of the black hole. From inside, as we have said, the experience is different. The falling person does not feel time stop. They continue to experience the passage of time normally, from their own perspective. But the time they experience, and the time experienced by someone far away from the black hole, have become disconnected, running at different rates, unable to be synchronized. This disconnection of time between different regions of space-time is one of the deepest and strangest features of general relativity, and black holes bring it to its absolute extreme. It is worth pausing here to appreciate something that often gets lost in popular explanations of black holes. The weirdness of black holes is not a special property of black holes alone. It is an extreme manifestation of properties that space-time has everywhere. Gravity always slows time. The curvature of space-time always bends the paths of light and matter. Virtual particles always fluctuate in the vacuum everywhere. The equivalence of mass and energy that underlies the conversion of mass to energy in Hawking radiation is always true. Everywhere. Black holes are extreme, but they are extreme versions of things that are always true about the universe. They are, in a sense, laboratories for the most fundamental physics, places where the ordinary properties of reality are turned up so high that they become impossible to ignore. Understanding black holes is therefore not just understanding one unusual type of object. It is understanding the fundamental properties of the universe in a regime where those properties are pushed to their limits and become unmistakable. You have one more thing to say, one more layer to add to this explanation, one that concerns not the physics of black holes specifically, but what they represent in the larger story of how a universe like this one came to be. Black holes are, in a very real sense, intimately connected to the existence of everything else. The supermassive black holes at galactic centers have shaped the galaxies in which stars form. Stars which produce the heavy elements that make planets, and, on at least one world, life. The stellar mass black holes are the endpoints of the most massive stars. The stars that lived fast and died explosively, and in doing so, seeded the galaxy with heavier elements. The gravitational waves produced by merging black holes and neutron stars carry away energy and allow the orbits of these objects to decay and lead to their merger, which in the case of neutron star mergers produces enormous amounts of gold and platinum and uranium and other heavy elements scattered into space, elements that eventually find their way into new solar systems. The physical processes that created black holes, and that black holes participate in, are woven into the history of the cosmos, into the creation of the conditions that make complexity and chemistry and life possible. A black hole is not separate from the story of the universe. It is embedded in it, connected to it, part of the great cycling of matter and energy and information that the universe has been engaged in since the first moments after the Big Bang. When a star collapses and forms a black hole, that is not the end of the story. The supernova that accompanies it seeds the surrounding space with elements. The jets powered by the newly formed compact object stir the surrounding gas. The gravitational influence of the black hole shapes the dynamics of the stellar environment around it. The Hawking radiation it will eventually produce, over timescales longer than the current age of the universe, will return its energy to the cosmos in a different form. Even the most complete, most locked-away object in the universe is, over long enough timescales, engaged with everything else. And perhaps that is the most important thing to understand about black holes, and indeed, about the universe in general. Nothing is truly isolated. Nothing is truly separate. The universe is one system, one interconnected process, and every part of it affects every other part, across all scales of space and time. A black hole seems like the ultimate expression of isolation and separation, a region from which nothing escapes, from which nothing communicates, which swallows everything and gives nothing back except a faint quantum glow over timescales longer than the age of the universe. And yet even the black hole is part of the whole, shaped by what fell into it, shaping in turn the space around it, connected by the space-time curvature that radiates outward from it, communicating through the gravitational waves it produces when it moves or spins or merges, participating in the grand story of a universe that has been telling itself for nearly 14 billion years, and has very much more to tell. If you had to summarize what a black hole is, for the curious inhabitants of this small, moist world, without any mathematics, without any equations or numbers beyond the simple ones needed to give a sense of scale, what would you say? You would say that a black hole is what happens when gravity wins. When a star so massive that its nuclear fires burn bright and hot and then go out. When that star collapses and nothing stops the collapse. When the matter falls inward faster than anything can push back. When gravity overwhelms not just matter and radiation, but the very geometry of space. When the curvature of space-time around the collapsing core becomes so severe that every possible path forward leads inward, that is when a black hole is born. The event horizon that surrounds it is not a wall. It is a horizon, in the truest sense of that word, a boundary beyond which you cannot see, not because your vision is limited, but because no light ever comes back from beyond it. The singularity that lies within is not necessarily a point in space in any ordinary sense. It is something stranger, something that the best current theories cannot adequately describe, a place where space-time itself may cease to have meaning in the way we know it. And the black hole as a whole is not empty space. It is the most extreme concentration of gravity in the universe, a place where the rules that govern everything else reach their limits, where the known meets the unknown, where the universe shows its depths and invites the curious to look deeper. This is what an alien, patient and ancient, and accustomed to the long view of cosmic time, would want you to understand about black holes. Not the equations, not the tensors, not the topology of embedding diagrams, but this, that the universe is capable of something this extreme, something this strange, something this beautiful in its darkness and its silence, that the cosmos contains places where time stops and space ends, and all directions point the same way, that these places are real, that they have been found and measured and listened to, that they are part of the story of how everything came to be, and that understanding them, even imperfectly, even in the incomplete way that any young civilization understands them, is a profound act of curiosity, the reaching of a small, young mind towards something vast and deep and genuinely wonderful. The universe rewards curiosity, not always with easy answers, often with harder questions, but always with the gift of deeper strangeness, with the revelation that reality is richer and more intricate and more surprising than you imagined. Black holes are, in this sense, one of the universe's greatest gifts to the curious. They are the universe saying, look, here is something you would never have predicted on your own, something that falls entirely outside your everyday experience, something that stretches every intuition you have to the breaking point, something that reveals the deep structures of space and time and matter that lie beneath the ordinary surface of things. You found it. You understood it, at least partially. You should be very proud, and you should keep looking